What is up, AS Math? It is Mr. Knight again. How's it going? Hope you guys had a really good break. Happy 2021. We're back in the saddle. We are starting our trigonometry unit today, actually. So, yeah, let's get right to it, okay? So here's our main topic for today. It's trigonomic functions and special right triangles. What makes them special, you ask? Well, let's find out, okay? First of all, hopefully you guys responded to that bell work and you got some cool ideas of what trigonometry is. Here's my rough definition of it. Trig. It is the relationship between the side lengths and angles of triangles. That's really it. We specifically like to look at right triangles a lot because they're a lot easier to work with, as you're going to see in a little bit, okay? So for all extensive purposes, right triangles are the only triangles we're going to be focusing on, okay? And so let's start with the trig functions. We've talked about these a little bit, and you probably have seen them in like in geometry classes before. But really what trig functions do is they are the relationship. They relate the angle and side lengths of triangles. And we do it with three trig functions, which we can remember with SOHCAHTOA. If you guys have ever seen SpongeBob, you know when they turn into superheroes and Squidward's that Krakatoa guy. That's how I remember it, if you need a reference on how to remember it. When all you have is an angle and a side, and you have to find the missing side length, SOHCAHTOA. Okay? Thank you, random person on the internet that made this. It's going to come in handy, okay? Because it's an acronym for our three functions. So if we have this right triangle right here, we have this angle theta that we call it, basically what we could do is we could label these side lengths a little bit more. So from this angle being the reference, this side is the opposite side, call it op. Adjacent means like next to, so it'd be this adjacent side. And the reason the adjacent side isn't this side is because that is the big boy right there. That is our hypotenuse right there, okay, our longest side length. So these trig functions kind of relate all those side lengths together based off this angle. So for example, it's sine is opposite over hypotenuse. That's why they call it so. And it's for our sine. So I kind of scribbled it out, but sine theta should equal your opposite side over your hypotenuse side. Okay? And that's just what sine does. It just relates those sides to that angle. Okay? We could also do it with cosine. A cosine is adjacent over hypotenuse. And tangent, the last one, which is tangent, is opposite over adjacent. Okay, so definitely get those down because, well, that's kind of the basic parts and building blocks of trig. If we can't do that, we really can't get too far. Let's talk about this triangle just a little bit more, specifically with sine and cosine. So, if this angle is right here, then I know what this angle is right off the bat. This angle has to be 90 degrees minus whatever angle this is. And that kind of makes sense, right? A triangle is made up of 180 degrees total. And already 90% or 90 degrees of that is taken up by this right angle. So if I have another angle like 20 degrees, I know this has to be 70 degrees. 90 minus 20 is 70 degrees. So these are how we kind of can relate them a little bit further. And that kind of brings up something a little interesting because if I do sine of 90 minus theta, of 90 degrees minus theta, well, that's technically, okay, that would be the opposite over hypotenuse if it's sine, but that would be the same thing as if I just did cosine theta right here, adjacent over hypotenuse, right? Sine of 90 minus theta is adjacent over hypotenuse, technically. So that's interesting. Sine 90 degrees minus theta is just equal to cosine of theta. So that's another one of those trig identities that kind of go along with these three right here. It's probably going to be useful. Not super useful today, but let's keep it in mind moving forward, okay? Now, let's talk about some special right triangles and what makes them so special. Special right triangles, these are triangles with specific angles. The reason these ones are specifically chosen is because they're actually really nice angles to work with, as you're going to see in a little bit. So here's my 30, 60, 90 degree triangle, and let's just assume for a second that I have a side length of 1 right there. Well, here's the thing about angles and sides is if I have like 30 degrees and that's a side length of 1, and then I double that angle, well, that doubles my side length as well. So right off the bat, I know that this guy right here, excuse me, actually, this is just going to, I'm sorry, scrap what I just said. It actually did not like matter at all what I just said. Let's rewind a little bit, okay? I promise I know what I'm talking about, but I just assumed something very, very wrong, okay? Let's assume, though, this is 1. We're going to call this side length 2, okay? Well, now let's see what this side length has to be using Pythagorean's theorem, okay? So what I could do is use Pythagorean's theorem in order to find that side length, and if I do this, I'm going to call A my 1, I'm going to leave B as B, I'm going to call C my hypotenuse 2. Let's see what we end up getting. So I get B squared equals, this is going to be 4 minus 1, and so that equals 3. And so I square root both sides, I get B equals square root of 3. So these are actually like the base ratios of like triangles with these angles. So for example, like if I had 2 right here instead, then this side length would be 4, and this one would be 2 square root of 3. That's kind of how it works, okay? Now, what I want us to do is I want us to create like a chart of all the important angles and the 3 trig functions and what happens when we plug that angle into that trig function. I call this the trig functions and common angles chart. It is a working title. It really rolls off the tongue. So what we're going to do is we're going to fill that stuff in with 30 and 60. So 30, I know if I'm starting at sine of 30 degrees, that's going to be opposite over hypotenuse. So sine of 30 degrees is 1/2. Okay. Cosine of 30 degrees is adjacent over hypotenuse, so that is square root of 3 over 2. Basically, that means if I just do sine of 30 degrees, I'm going to end up just getting 1/2 without even using a calculator. It's really nice. And finally, tangent. Tangent of 30 degrees is opposite over adjacent, so that's going to be opposite over adjacent, so 1 over square root of 3. Nice. Okay. Let's do it with 60 degrees real quick. Opposite over adjacent, or opposite over hypotenuse for sine. Sine of 60 is square root of 3 over 2. Cosine of 60 is adjacent over hypotenuse, so 1/2. And then for this guy, the tangent of 60 degrees is going to be opposite over adjacent, so it's square root of 3 over 1, which is just square root of 3. We're going to leave that chart as is right now. We'll fill it out as we go. All right. With 30, 60 degree, 90 degree triangles, let's just find the value of this right here, of cosine 60 degrees sine 30 degrees plus cosine squared of 30 degrees. We're going to do it without a calculator and see what we get. So let's do that. Spoiler alert, 45 degrees will be incoming soon. Okay. So let's take a look at this guy. Again, we know cosine 60 degrees based off our chart is just 1/2. I also know that sine of 30 degrees, just by looking at my chart, is going to also be 1/2. That's kind of nice. Plus, we have this cosine squared of 30 degrees. Now, I want to make this very clear. Cosine squared of 30 degrees is the same thing as just cosine 30 degrees squared like that. So we have to do cosine of 30 and then square it, okay? Which is much different than them writing it like, you know, they might write it like cosine of 30 degrees squared like that. If they write it like that, you are doing 30 squared. You're doing cosine of 900. You're pretty much never going to see it written like that. But that's why they write it like this, so that you can differentiate between those two things. So just keep that in mind. Anyway, cosine of 30 degrees is square root of 3 over 2. And of course, we need to square that. So we need to square the top and the bottom. So let's see, we get 1/4 plus square root of 3 is, well, squared is just 3 over 4. And so that's going to equal just 4 over 4. Huh, who would have thought? Not me, okay? Luckily for us, we have some good trig functions that can help us out and make that a lot simpler of a process. Let's continue on. Let's look at the other one, 45, 45, 90 degree triangle. Kind of the same idea with 30, 60, 90. It's just now we have a different angle, right? So if I have 45, 45, 90, if I make, again, this side length down here 1, that means this side length across from this 45 also has to be 1. And I can find the hypotenuse side length, what it should be, with Pythagorean's theorem. So 1 squared plus 1 squared equals c squared. Take the square root of both sides. You end up getting square root of 2 equals c. Which is really, really handy, once again, because now we can add on to our chart. Let's do that. Because now we can do sine of 45. Well, sine of 45 is just going to be opposite over hypotenuse. That's 1 over the square root of 2. And then we could do cosine of that. Well, that's adjacent over hypotenuse. It's the same exact thing. 1 over square root of 2. And then finally, tangent is going to be opposite over adjacent. 1 over 1, which is 1. Which is pretty nice. That's actually the nicest one out of all of them so far. So now we're missing just 2 angles, 0 degrees and 90 degrees. Now, if we think about it, we can't have an angle of 0 degrees. Doesn't really make sense. We also can't have two 90 degrees in our triangle because that would be impossible. It wouldn't even be a triangle at that point. But we can think about what would happen is if those angles get really close to 0 degrees or 90 degrees. Okay, so let's take a look at that. We'll call this our third case. It's not a special triangle. I'm going to say not special, which, I mean, if you guys really want to make it special, you're allowed to, but it's not really a triangle. This is more of a thought experiment, okay, but it's still going to be handy. So let's assume for a second, let's assume that the hypotenuse is just a length of 1. Let's also assume that this angle theta right here is going to 0 degrees. It doesn't equal. It's going to 0 degrees, and this angle alpha is going to 90 degrees, okay? And let's think about this for a second. So if I am getting really, really close to 0 degrees, okay, my hypotenuse length is not going to change, okay? Hypotenuse length will not change. This opposite side absolutely will change. Because if this gets even smaller and smaller and smaller to 0 degrees, maybe it's better to just do it like this with my hands. If I get really, really close to 0 degrees, well, what ends up happening is this opposite side length between my fingertips ends up going to 0, right? So if I think about sine of theta, sine of 0 degrees in this case, so I'm just going to replace it with sine of 0. I know that my opposite length is going to end up going to 0, and then over, you know, the sine is opposite over hypotenuse, so my hypotenuse length is still 1. So that means sine of 0 degrees is just 0. Let's record that on our chart. Sine of 90 or sine of 0 degrees is just 0. Okay. We could also do it with cosine. Again, this length down here, as this side gets really, really, really small because of this angle, this adjacent side does not change its length, just like the hypotenuse. So we end up getting and they'll kind of be like sandwiched on top of each other. So the hypotenuse and adjacent sides are almost equal, which means cosine of 0 degrees is really 1 over 1, which just equals 1. Okay? Cosine of 0 degrees is 1. And lastly, let's talk about tangent with it. Okay, I have now my opposite over adjacent side. Again, this is going to be 0 over 1. Because we just saw it with sine and cosine. So tangent of 0 degrees is just 0. All right. Okay, well now we can think about it going with 90 degrees. That's where the alpha angle is going to come in handy with this thought experiment. Because as this guy goes to 0, this side, it's got to compensate for that. The triangle has to maintain being 180 degrees total with its angles. So to compensate, it goes to 90 degrees, which is a little bit harder to visualize. So I'm just going to help you out a little bit, all right? I'm going to tell you that sine, or no, that sine of 90 degrees, it kind of flip-flops with cosine and sine. Sine of 90 degrees is ended up going to be 1. Cosine of 90 degrees is going to end up being 0. It'll be more apparent once we get to the unit circle, so don't worry so much about wrapping your head around that right now. Tangent of 90 degrees is very interesting. You end up getting 1 over 0. which ends up being undefined. Okay, so we can't actually use that guy yet. But we can use this chart to help us with these initial trig problems. So let's look at one more example, kind of tying all this together. I really just want us to get more practice, or any practice using trig, because some of us, I don't think, have ever learned it before, which is pretty sweet. So it's a cool opportunity. Or it sucks if you hate math, I guess. One way or another, I think we're going to be okay. Let's look at this example. So we have these two triangles chilling by each other. We have angle ADB and CBD. These guys are just right angles. That's all that's saying. We know angle BAD is going to be 60 degrees. AB, the line segment AB, is 2L. So they're not giving any specific units. They're just saying it's L. It's some constant. And BC is also 3L. Our goal is to find angle theta right here, okay? Just given this information. Well, let's see what we can do here. We probably, because we have some kind of side length given to us here in terms of L with this triangle, we probably want to get one of these guys to have their line segment. I would go for this guy, mostly just because it's related by both these triangles, right? So let's start out finding that side length using this angle. So to get that angle, let's see. It looks like if we related it with opposite over hypotenuse, we could get it, and that would be sine. So if I do sine of 60 degrees, that's going to be equal to opposite, which is just x for right now, we'll call it, over hypotenuse, which is 2L. Okay. Well, to get that side length, what I can do, first of all, I could actually just do sine of 60 degrees, which we know with our chart is square root of 3 over 2. So I'm going to turn that into square root of 3 over 2 equals x over 2L. Well, now I want to get the x by itself to solve for that length, so I'm going to cross multiply. I'm going to say 2x equals 2L square root of 3. And then finally, I need to divide both sides by 2. And so I end up getting x is equal to the square root of 3L. Okay? Well, now that I know what that is, I'm going to put it in. So I have it. And now I can work with this top part with this angle. Okay? So that angle right there, the relationship between these sides is going to be, it looks like we have opposite over adjacent. It's our hypotenuse. So that is going to be tangent of theta. And that's going to be equal to square root of 3L over 3L. Well, that's kind of nice. The L's will end up canceling. See you later. And I'm left with tangent theta equals square root of 3 over 3. Now, we want to find what that angle theta is. Okay? There's a couple things we can do. First of all, we can use a calculator. What you can do with a calculator is you can take the arctangent of both sides, and you'll end up getting theta equals the arctangent of square root of 3 over 3. Just make sure you're in degree mode. The other thing we can do is look at our chart. Is that a known value? It doesn't look like it. Doesn't look like it, but it is. Okay. There's some alternative forms of these guys that I didn't write down. For example, this guy. If I have 1 over square root of 3, and I want to radicalize the bottom, like I don't want a square root, I could take the square root of 3 and multiply the top and the bottom of that fraction, and I can get square root of 3 over 3 as an equivalent value. Likewise with these guys down here, this is square root of 2 over 2, and square root of 2 over 2 for these guys. Okay? That's another way you can look at it. So actually, we know what that angle is. That angle is tangent of 30 degrees. So angle is 30 degrees. Okay, that's all there is to it. All right. Good luck on your homework. It was good making a video for you guys again. Some things never get old, and I will see you guys very soon. Hopefully we do that Zoom conference, and we can talk about this stuff if you need help. Okay.